In this video, we will be talking about inductors. Anytime that current flows through a wire of any sort, you will have a flux line that will form around the wire and create the electromagnetic fields which tries to push against the electrons as they move through the wire. This effect more or less will create inductance in the wire. Now, a straight line won't have much inductance, so if you're really after creating inductance, a lot of the times we will have to wind the wires to create more flux. In this case, you will have a lot more flux coming out of these wires because there's more wires as the current is flowing through it. This is typically how inductors are built. Now, sometime you will find that we will put a core material that is a conductive material inside, and then we would wound the winding around that. The purpose of that is to make sure that we keep the flux around the wire, so we make for a more efficient way of building transformers. Although the conductive core is not absolutely necessary, you can make inductors with the core being air, but it would be more efficient if the core was metal. So this is more or less the physical construction of an inductor, is a winding of a conducting wire around a core. And the symbol actually kind of looks like that. So the symbol for inductor in a circuit will be basically a line and a few rows indicating it's a winding. And then again, is a passive device, which means if a current is flowing in this direction, by definition it would follow the passive convention and it would have voltage coming across it. Inductance is measured by a unit called Henry, and we represent inductance with an L, so that's the letter that is reserved to indicate inductors. Okay, now the relationship, as we meant in one of the previous presentation, we talked about the relationship that is created. It's the change in current equal to change in flux, and change in flux is actually voltage. So we will write V of t equals to L d I dt over t. And this is a very important equation. This allows us to relate current and voltage to inductors. This is as important for inductor as Ohm's law was for resistors. Of course, current, as always, is going to be in amp. Units of current will be in amp. Units of volt would be in voltage would be in volt, and L would be in Henry or Henry's L, and represented by L. Okay, so that's a relationship we need to have. Some couple of things to notice is that if I of t is not changing, is constant, that means there is not going to be a voltage in the inductor. So the inductor depends on the current, and the current in the inductor to change in order for it to create a voltage. So this is an important concept to remember, that the voltage is dependent on the slope of the current. So for example, if we have an I of t, and that I of t, let's say, is represented by a flat and then slope down, you will find the place where the current is flat, the voltage, the resulting voltage in the inductor is actually going to be 0. The only time it starts to change, and in this case is going down, so the voltage will start to be created based on here. So and the level of the current, whatever the slope is here, that slope would be the voltage you're going to be generating across the inductor. Okay, so that's as far as that goes. Of course, we can also take this one step further and start looking at the opposite. Say, okay, well, if I have an inductor and I want to find out the I, but I have the voltage, how do I do that? Well, in order for you to do that, we can take an integral of both sides. So we'll have 1 over L integral of voltage they usually change this to a tau, replace the variable with tau, derivative of tau, and this thing will go from an initial time, sometime when we start tracking it, to present time, or the time you want to find out what the current is. Now you have to also add to this one an initial condition. So that's a new one compared to what we've done before. So you have to know what the initial condition of the inductor is, how much current is in there when you start your process. Otherwise, you would not be able to write the total current. So this is an important one, but we're not too excited about this, because anytime we have this equation, we can always find the opposite, which is an integral of both sides. Okay, so that's that. Well, before we go too far, let's go ahead and do one more thing. Energy is a really important, energy and power is really important for energy. For us, it's pretty important. So what we do, and by the way, this is either going to be represented as work with respect to time or E of time. Don't confuse E of time with E to the power of something, where E is 2.7 roughly. So that's a common mistake. So energy sometimes represented this way, sometimes represented this way. So in power with respect to time is defined as the change of energy with respect to time. Okay. We could, or vice versa, we could say energy or work is equal to the integral of power, because power is energy for a second. So over time, so if you average it, that would happen. So now power, we always know power is I of t times V of t. So I suppose I could replace this with the newfound equation for inductors. We can rewrite this as I of t, and then the V we can write as L di dt. And the whole thing is an integral with respect to time. So if we clean this up, we'll find out this is simply 1/2 Li of t squared. So that's kind of nice to remember, that the energy was stored in an inductor, or work in this inductor to a given point in time, and simply 1/2 Li squared. Okay, and the units, of course, for energy is joules. And as we have talked about before, power is watts. So that's as far as it goes. There was really not much new here, other than the introduction of us to inductor, how it's built, and then very, very important relationship. This should be a relationship that it's very important, got to be in the tip of your tongue. V is equal to L di dt, because that's as important to inductors as Ohm's law was to resistors.